In this video, we are going to discuss the structure, the physical structure and the operation of the bipolar junction transistor in the active region. Mainly, we are going to focus on the NPN transistor, and the PNP will be very similar to the operation with reversing everything. So instead of talking about electrons, we'll be talking about holes. So all the currents and voltages and charges will be reversed. So let's focus on the NPN first. We have the structure of the bipolar junction transistor. It has three regions: emitter, base, collector, and this is N. The base is P, the collector is N. So this is full of electrons, negative charge. This is full of holes, positive charge, and the collector is N. So it has a majority carriers of electrons. In order to operate the transistor in the active region, we need to connect the emitter base junction to be forward bias, which means that we connect the emitter to a negative voltage and the base to a positive voltage that is greater than 0.6 or 0.7, which is the operation or the operating voltage of the diode, because the emitter base junction is basically a diode, right? So we need to connect the voltage in this direction between the base and the emitter. We call it VBE. And this VBE must be greater than 0.7 in order for the diode between the emitter and the base to operate. While in order to keep the junction between the base and the collector reverse bias, and this is a condition for the active region, is that this junction is forward bias and this junction is reverse bias. In order to keep this junction to be reverse bias, you need to connect the base to a negative voltage and the collector to a positive voltage. And we can call this voltage VCB. So now, we guarantee by this connection, we guarantee that the emitter base junction is forward biased, the collector base junction is reverse biased. By the way, just for your information, in order for the transistor to operate in the active region, you don't have to have this junction to be reversed. You need at least that it is not forward. You need at least to guarantee that this junction is not forward biased. Okay? So it's enough to guarantee that this junction is not forward biased. So not necessarily it's reverse biased, but at least you guarantee that it is not forward biased. Okay? This is just for your information, and we'll use this later. But now, using this setup, the emitter base junction is forward, the collector base junction is reversed. Let's now see what happens. As a physical structure, as physics, let's see what happens. Let's focus on the emitter base junction. You connected this junction in the forward bias region. So what happens is electrons will start to cross from the emitter to the base. So there will be electrons crossing in this direction. Electrons. I'm going to plot the electrons in this purple color. So these are electrons crossing from the emitter to the base, and there will be holes crossing from the base to the emitter, right? This is from our study of the diode, from our study of the structure and the physical structure and the operation of the diode. We understand that if you have a junction connected in a forward bias, then using the diffusion, electrons will flow from the high density or high concentration to the low concentration, and holes will flow from the high concentration to the low concentration. So holes will flow from here to here. These two components, they will compose the emitter current. So you can say that the emitter current consists of two components. Emitter current that comes from the electrons that cross from the emitter to the base, and emitter current that comes from the holes that cross from the base to the emitter. The summation of these two components gives the emitter current. And we know that from the diode, again from our study of the diode, that this current, emitter current, is proportional to exponential VBE over VT, right? This is the current of the diode. The current of the diode is proportional to exponential the voltage of the diode, which is VBE here, over VT, which is the threshold voltage. So this is the first equation, is that the emitter current consists of the electrons that will cross from here to here and holes that will cross from the base to the emitter. However, the first information that you should know is that they designed the transistor. They designed the transistor so that the holes that will cross from the base to the emitter, this component of the holes is much smaller than the component of the electrons that cross from the emitter to the base. Why is that? Because they want most of the emitter current to be in this component for a reason that I will mention later. So most of the electron current, they design it to be in the electrons crossing from the emitter to the base. While the holes crossing from the base to the emitter, they try to keep it as small as possible. This component, how is that? How they keep the holes crossing from here to here as small as possible? By reducing the doping of the base. So they reduce the doping of the base to be very small compared to the doping of the emitter, and hence the diffusion current that comes from the holes, the concentration of the holes first will be small. If the doping is small, the concentration of the holes will be small, and then the component of the current crossing from the high concentration to the low concentration will be also small. So they design the doping of the base. Doping of the base is small so that the component of the IE from the holes is very small compared to the other component. And hence, we can say that the emitter current approximately will be coming from the electrons crossing from the emitter to the base. Okay, so this is the first information that we should know. Now what happens to these electrons? What happens to these electrons that will cross from the emitter to the base? Of course, we learned that some of the electrons here in the base, by the way, they will be considered as minority carriers, right? So that these electrons that will exist in the base, they will represent minority carriers in the base, right? Some of them will recombine with holes. So some of the electrons recombine with holes in the base. So some of them will recombine with holes. And we remember that there is something called recombination rate. Some of the electrons, they recombine with holes and they disappear. The electrons and the holes not disappear, they become not free to move anymore, right? So some of the electrons will recombine with holes, electron negative and the hole positive, and hence the electron will fill the hole and stop moving. So some of the electrons will recombine with holes. What about the rest of the electrons? In order to understand what happens to the remaining electrons, let's look at the second junction, the base collector junction. The base collector junction is reverse biased. Reverse biased, which means that there is a depletion region, big depletion region here. Depletion region increases, okay? And if you remember, if we connect a junction or a diode in reverse bias, what happens? You remember that we had a very small current in the diode, we had a very small current called the saturation current, and this saturation current, if you remember, in the diode, it comes from the minority carriers. So in the diode, when we had Pn, okay, here we have a lot of positive charges, here negative charges, but we had some minority carriers here negative, and some minority carriers here to be positive. When we connected the diode in a reverse bias like this, what happened is the depletion region, of course, increased. We had a big depletion region, okay? And then we said that there will be a leakage current. There will be a very small current. This small current comes from where? It comes from the minority carriers. So when you connect the negative to the P, the negative charges in the P, which are the minority in the P, these are the charges that will flow to the other side. And the minority carriers in the N, which are the positive charges in the N, these are the charges that will flow to this side. So the current under reverse bias, the current is based on the minority carrier charge type. Let's look here at our example. Now the electrons that crossed from the emitter to the base, they represent minority carriers in the base. When you connect the base collector junction in a reverse bias, what happens? What happens is that these minority carriers will continue moving to the collector because they are minority carriers. And we said that under reverse bias, the minority carriers here will cross to the other side. So the remaining electrons here will cross because they are minority carriers, and this junction is reverse bias. The minority carriers will cross to the other side. In addition, of course, if you have any minority carriers here, like some positive charges, they will cross also to the base, but usually we ignore the minority carriers here because they are very small compared to the minority carriers here, which are now high because they came from the emitter. The minority carriers here in the base now, they have high concentration. Why? Because they crossed from the emitter, right? So we have high concentration of electrons, and these electrons are still minority in the base. So when you connect the base collector junction in a reverse bias, these minority carriers, these electrons will cross to the collector. In addition, some of the minority carriers or the minority carriers in the collectors which are positive charges here will cross to the base, but we usually ignore these minority carriers that cross to the base. Anyways, let's now think about the base current and the collector current. The base current will consist of what? The base current, you need to supply the base with positive charge to support this current and to support the recombination, the holes that recombine with electrons. So the base current is supposed to be of two components again. Some holes to cross, to replace the holes that cross to the emitter, and some holes to replace those holes that recombine with electrons. So this is the base current. The base current basically will be some holes to replace the holes that cross to the emitter, and some holes to replace those holes that recombine with electrons. However, again, we said that this hole or this component is small. They designed it to be small. And also they designed the other component, the recombination, to be very small. How would they do that? They do that by making the width of the base to be very small. The width of the base very small, this will reduce the recombination rate. If the width of the base is very small, then most of the electrons that will come to the base, they will cross to the collector without recombining with holes. So they designed the base to be with a small width to reduce this recombination rate. So the recombination is very small, and hence the two components of the base current, both of them are very small. And this is what we want. We want the base current to be very small. Why? Because the base current is just a control signal. It's a control signal. You use it to control. You don't want the base to take current from the emitter or the collector. You want the base current to be just a control signal, and if you can make it zero, this is the perfect thing. Okay, if you can, but practically we cannot here. But you want to reduce it as small as possible so that you make the collector current and the emitter current almost the same. So you use it as a control, and then the current will pass from the emitter to the collector as it is, or it will not pass. So you want the base current to be as small as possible because this is just a control current. You don't want the control current to be of high value, and you want to use it just to control whether the current will flow from the collector to the emitter or not, right? If you can make it zero and you make the collector and the emitter current to be the same, exactly the same, that would be perfect. But unfortunately, in practice, we cannot. So we reduce I base as much as possible by two things. We reduce the doping of the base to reduce this component of holes crossing from the base to the emitter. We reduce the width of the base to reduce the recombination rate of the recombination rate of the base or in the base. Okay, that's why here the two components, both of them of the base current, both of them are small, and hence the base current in general is very small. Okay, we'll stop here in this video to make it short, and then we'll continue in the next video, inshallah.